3.3, real zeros of polynomials. We have p of x equals x minus 2 times x minus 3 times x plus 4. Now this is called its factored form. If we were to multiply this out, we would get x squared minus 5x plus 6 times x plus 4, and that becomes x cubed minus x squared minus 14x plus 24. This form is called the expanded form. But when we can see the factored form, we can get our zeros. And those are 2, 3, and negative 4. But when we see the expanded form, we can see that the constant 24 is found by multiplying to negative 2 times negative 3 times 4, which are the opposites of the zeros. So this means that the zeros of the polynomials are all factors of the constant term. So this brings us to a general observation named the rational zeros theorem. If the polynomial p of x equals a sub n x to the n plus a sub n minus 1 to the x to the n minus 1 all the way down to a sub 0 has integer coefficients, then every rational zero of p is of the form p over q, where p is a factor of the constant coefficient a sub 0 and q is a factor of the leading coefficient a sub n. So in general, we want to factor our constant term over a factor of our leading coefficient. So when we are finding the rational zeros of a polynomial, we list all the possible zeros using the rational zeros theorem. We find one by dividing using synthetic division, and we repeat steps 1 and 2 for the quotient, and we stop once we reach a quadratic or something that factors easily. Then we find all of our zeros. Okay, so we are going to factor the polynomial p of x equals 2x cubed plus x squared minus 13x plus 6. We're going to use the zeros and end behavior to sketch the graph as well. So, a sub 0 is 6. A sub n is 2. So we need to list all the factors of 6, which are 6, 2, let's go 6, 1, 2, and 3. And the factors of 2 are just 2 and 1. So we need to list all the possible fractions. We could have plus or minus 1 over 1 right here, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1, plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, and plus or minus 6 over 2. And you'll see that simplifying some of these fractions will eliminate repeats. So we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, and plus or minus 3/2. Okay, so now we check these possible zeros. This is a list of all possible zeros. So now we evaluate them, as we learned in section 2, to see if they are zeros. So we go, let's start with P of 1. And if it comes out to 0, then it is a factor. If it does not, then it is not a factor. Plug in 1 for x, 2 times 1 cubed plus 1 squared minus 13 times 1 plus 6. When we work that all out, you get -4. So 1, not a factor. Okay, let's try 2. And you just continue trying until you find one that is a factor. So P of 2 goes 2 times 2 cubed plus 2 squared minus 13 times 2 plus 6. And you do get this to go to 0. So this means that 2 is a factor of 0. So since we know that x equals 2 is a 0, we can use synthetic division to work this out. So we go 2, 1, -13, 6. Use synthetic division. And it comes out to 0 remainder, which is exactly what we wanted. So we get 2x cubed plus 5x minus 3. And we can actually factor this, and it's going to become x plus 3 times 2x minus 1. So these are two factors, and then we had our original third. Bring it down into the form x minus c, which goes x minus 2. So that is completely factored. So let's do one more where we have to find all the zeros of the polynomial. We have p of x equals x to the 4th minus 6x to the 3rd plus 4x squared plus 15x plus 4. So possible solutions. A sub 0 is 4, which is 1, 2, and 4 for its factors. A sub n is 1, and 1 is 1. So our possible factors and we always go positive and negative, -1, 2, and 4. if we try 1, goes 1 to the 4th minus 6 times 1 plus 4 times 1 plus 15 times 1 plus 4. So 1 minus 6 plus 4 plus 15 plus 4. That does not equal 0. So 1 does not work. So let's try negative 1. Negative 1 to the 4th minus 6 times negative 1 cubed plus 4 times negative 1 squared plus 15 times negative 1 time plus 4. We get 1 plus 6 plus 4 minus 15 plus 4. 1 plus 6 is 7 plus 4 is 11 minus 15 is negative 4 plus 4, and it goes to 0. So x minus 1 is a factor. So now we're going to use positive 1 and use synthetic division. Oops, that should have been a negative 1 out there. X plus 1 is a factor. Negative 1. Sorry. Wow. Swear, I know how to do this. There we go. Now we get 0 remainder. So we are now at, highest degree was 4. We're now at a 3. So x cubed minus 7x squared plus 11x plus 4. So we get here, and we see this is not factorable. So we have to, once again, try the possible zeros. Happens to have the exact same possible zeros as before. Positive and negative 1, positive negative 2, and positive negative 4. So P of 1, 1 cubed minus 7 times 1 plus 11 plus 4 times 1. 1 minus 7 plus 11 plus 4 doesn't work. Let's try P of negative 1. Goes negative 1 cubed minus 7 times negative 1 squared plus 11 times negative 1 plus 4. Negative 1 minus 7 minus 11 plus 4 doesn't work either. So you go to 2. Two cubed minus 7 times 2 squared plus 11 times 2 plus 4. So 8 minus 28 plus 22 plus 4. Looking at the problem, negative 2 will not work either. So let's try P of 4. 4 cubed minus 7 times 4 squared plus 11 times 4 plus 4. So we get 64 minus 112. plus 44 plus 4. Let's see, 4 minus 112, negative 48 plus 44 plus 4 goes to 0. So one of our solutions is also x minus 4. And earlier we had x plus 1. So now we use 4 synthetic division once again. X cubed, so x, negative 7, 11, and 4. Synthetic division, 1, 4, negative 3, negative 12, negative 1, negative 4. Yay, it worked. So now this is x squared minus 3x minus 1. And we get down to a quadratic, but it's not factorable. So how do you solve non-factorable quadratics? By the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Three plus or minus 9 plus 4 over 2. So we get x to be 3 plus or minus the square root of 13 over 2, along with our two previous zeros, negative 1 and 4. So we do get 4 zeros that occur at negative 1, 4, and 3 plus or minus the square root of 13 over 2. If we were to use this to graph, we see negative 1, 4, use a calculator to approximate where those points lie. So we worked out with the calculator what these points come to for graphing purposes. Negative 0.3 and 3.3. We know our leading term was x to the 4th. So it is even and positive. So we know y approaches infinity as x approaches infinity. We also know y approaches infinity as x approaches negative infinity. And so you can test points. And you'll get a graph to make the W like mine.